The most widely used machine learning tool is today is supervised learning. Actually, let me check. How many of you know what supervised learning is? Like a 2/3, half of you maybe? Okay, cool. Let me just briefly define it. Here's one example. Let's say you have a database of housing prices, and so I'm going to plot your data set where on the horizontal axis, I'm going to plot the size of the house in square feet, and on the vertical axis, we'll plot the price of the house, right? And maybe your data set looks like that. And so horizontal axis, I guess we'll call this X, and vertical axis, we'll call that Y. So the supervised learning problem is, given a data set like this, to find a relationship mapping from X to Y. Right? And so, for example, let's say you're fortunate enough to own a house in Palo Alto, right? And you're trying to sell it, and you want to know how to price the house. So maybe your house has a size, of that amount on the horizontal axis. I don't know. Maybe this is 500 square feet, 1,000 square feet, 1,500 square feet. So your house is 1,250 square feet, right? And you want to know, how do you price this house? So given this data set, one thing you can do is fit a straight line to it, right? And then you could estimate or predict the price to be whatever value you read off on the vertical axis. So in supervised learning, you are given a data set with inputs X and labels Y, and your goal is to learn a mapping from X to Y. Right? Now, fitting a straight line to data is maybe the simplest possible, learning algorithm, maybe one of the simplest learning algorithms. Given a data set like this, there are many possible ways to learn a mapping, to learn a function mapping from the input size to the estimated price. And so maybe you want to fit a quadratic function instead. Maybe that actually fits the data a little bit better. And so how do you choose among different models will be either automatically or manual intervention will be something we'll spend a lot of time talking about. Now, to give a little bit more, to define a few more things, this particular example is a problem called a regression problem. And the term regression refers to that the value Y you're trying to predict is continuous. In contrast, here's a different type of problem. So a problem that some of my friends were working on, and I'll simplify it, was a healthcare problem where they were looking at breast cancer, breast tumors, and trying to decide if a tumor is benign or malignant, right? So a tumor, sort of a lump in a woman's breast, can be malign or cancerous, or benign, meaning roughly that's not that harmful. And so if on the horizontal axis you plot the size of a tumor, and on the vertical axis you plot is it malignant or not. So malignant means harmful, right? And some tumors are harmful, some are not. And so whether it's malignant or not takes only two values, 1 or 0. And so you may have a data set like that, right? And given this, can you learn a mapping from X to Y, so that if a new patient walks into your office, walks into the doctor's office, and the tumor size is, say this, can the learning algorithm figure out from this data that it's probably, well, based on this data set, looks like there's a high chance that tumor is malignant. So this is an example of a classification problem. And the term classification refers to that Y here takes on a discrete number of variables, right? So for a regression problem, Y is a real number. I guess technically prices can be rounded off to the nearest dollar and cent. So prices aren't really real numbers, because you probably not price a house at like pi times 1 million or whatever. But for all practical purposes, prices are continuous, so we call them housing price prediction to be a regression problem, whereas if you have two values of possible output 0, 1, we call that a classification problem. If you have k discrete outputs, so if the tumor can be malignant, or if there are 5 types of cancer, right, so you have 1 of 5 possible outputs, then that's also a classification problem if the output is discrete. Now, I want to find a different way to visualize this data set, which is, let me draw a line on top, and I'm just going to, map all this data on the horizontal axis upward onto a line. Well, let me just show you what I'm going to do. I'm going to use a symbol O to denote right. I hope what I did was clear. So I took the two sets of examples, the positive and negative examples. Positive examples is 1, negative examples is 0. And I took all of these examples and kind of pushed them up onto a straight line. And I used two symbols. I used O's to denote negative examples, and I used crosses to denote positive examples. Okay, so this is just a different way of visualizing the same data, but drawing it on a line and using two symbols to denote the two discrete values 0 and 1. Right. So it turns out that in both of these examples, the input x was one-dimensional. It was a single row number. For most of the machine learning applications you work with, the input x will be multidimensional. You won't be given just one number and asked to predict another number. Instead, you often be given multiple features or multiple numbers to predict another number. So for example, instead of just using tumor size to estimate malignancy or malignant versus benign tumors, you may instead have two features, where one is tumor size, and the second is age of the patient, and be given a data set. Maybe I'll sit. Right, and be given a data set that looks like that. Right, where now your task is given two input features, so x is tumor size and age, like a two-dimensional vector, and your task is given these two input features to predict whether a given tumor is malignant or benign. So if a new patient walks in the doctor's office, and if the tumor size is here and the age is here, so that point there, then hopefully you can conclude that this patient's tumor is probably benign, right, corresponding to O, the negative example. And so one thing you learn next week is a learning algorithm that can fit a straight line to the data as follows, kind of like that, to separate out the positive and negative examples, separate out the O's and the crosses. And so next week you'll learn about the logistic regression algorithm, which can do that. Okay. So one of the most interesting things you learn about is, let's see. So in this example, I drew a data set with two input features. So I have friends that actually worked on the breast cancer prediction problem, and in practice, you usually have a lot more than one or two features, and usually you have so many features you can't plot them on the board, right? And so for an actual breast cancer prediction problem, my friends are working on this. We're using many other features, such as, don't worry about what these mean, I guess, clump thickness, uniformity of cell size, uniformity of cell shape, right? Adhesion, how will the cells stick together? Don't worry about what these means. But if you're actually doing this in an actual medical application, there's a good chance that you'll be using a lot more features than just two. And this means that you actually can't plot this data, right? It's too high dimensional. You can't plot things higher than 3-dimensional, or maybe 4-dimensional or something, right? And so when you have a lot of features, it's actually difficult to plot this data. I'll come back to this in a second in learning theory. One of the things you learn about, so as we develop learning algorithms, you learn how to build regression algorithms or classification algorithms that can deal with these relatively larger number of features. One of the most fascinating results you learn is that you also learn about an algorithm called the support vector machine, which uses not 1 or 2 or 3 or 10 or 100 or 1,000,000 input features, but uses an infinite number of input features, right? And so just be clear, if in this example, the state of a patient will represent as one number, tumor size. In this example, you get 2 features. So the state of a patient will be represented using 2 numbers, the tumor size and the age. If you use this list of features, maybe a patient is represented with 5 or 6 numbers. But there's an algorithm called the support vector machine that allows you to use an infinite dimensional vector to represent a patient. And how do you deal with that, and how can a computer even store an infinite dimensional vector, right? I mean, computer memory, you could store 1 real number, 2 real numbers, but you can't store an infinite number of real numbers in a computer without running out of memory or process speed or whatever. So how do you do that? So when we talk about support vector machines, and specifically the technical method called kernels, you learn how to build learning algorithms that work with sort of an infinitely long list of features, and you can imagine that if you have an infinitely long list of numbers to represent a patient, that might give you a lot of information about that patient, and so that is one of the relatively effective learning algorithms for some problems. So I've been using an artificial neural network to drive this vehicle that was built at Carnegie Mellon University many years ago. And what happens is during training, it watches the human drive the vehicle, and I think 10 times per second, it digitizes the image in front of the vehicle. And so that's a picture taken by a front-facing camera. And what it does is, in order to collect labeled data, the car, while the human is driving it, records both the image, such as you're seeing here, as well as the steering direction that was chosen by a human. So at the bottom here is the image turned into grayscale and lower res. And on top, let me pause this for a second. This is the driver direction. The font's kind of blurry, but this text says driver direction. So this is the Y label, the label Y, that the human driver chose. And so the position of this white bar, of this white blob, shows how the human is choosing to steer the car. So in this image, the white blob is a little bit to the left of center, so the human is steering just a little bit to the left. This second line here is the output of the neural network. And initially, the neural network doesn't know how to drive, and so it's just outputting this white smear everywhere. It's saying, I don't know, do I drive left, right, center? I don't know. So it's outputting this gray blur everywhere. And as the algorithm learns using the backpropagation learning algorithm or gradient descent, which you learn about, you actually learn about gradient descent this Wednesday. You see that the neural network's outputs becomes less and less of this white smear, this white blur, but starts to become sharper and starts to mimic more accurately the human selected driving direction. So this is an example of supervised learning because the human driver demonstrates inputs X and outputs Y. Namely, if you see this in front of the car, steer like that. So that's X and Y. And after the learning algorithm has learned, you can then, he pushes a button, takes a hand off the steering wheel, and then is using this neural network to drive itself. Right? Digitizing the image in front of the road, taking this image and passing it through the learning algorithm, through the trained neural network, letting the neural network select the steering direction, and then using a little motor to turn the wheel. This is a slightly more advanced version, which has trained 2 separate models, one for, I think, a 2-lane road, one for a 4-lane road. So that's the so the second and third lines, this is for a 2-lane road, this is a 4-lane road, and the arbitrator is another algorithm that tries to decide whether the 2-lane or the 4-lane road model is a more appropriate one for a particular given situation. And so as Alvin is drawing, excuse me, a one-lane road or a two-lane road. So it says driving from a one-lane road here toward an intersection. The algorithm realizes it should switch over from, I forget, I think the one-lane neural network to the two-lane neural network, or one or three.